At this point, you've heard me talk about x86 instruction decoding. So we're going to go into more detail here. Modern x86 CPUs rely on instruction decoding stages to interpret machine-level instructions into microoperations the CPU can execute. This process is critical for efficient execution of code, and it plays a key role in performance optimization and security monitoring. Now, you may recall the x86 architecture is a family of instruction set architectures, ISAs, originally developed by Intel. It was introduced in 1978 with the Intel 8086, and it's used in most consumer PCs, servers, and cloud infrastructure, and it's known for its complex instruction set computing, CISC nature, which supports variable length instructions. The x86 ISA uses these variable length instructions like 1 to 15 bytes, making instruction decoding more complex than in the fixed length ISAs like ARM. This complexity requires multiple decoding stages, ensuring efficient CPU operation. The CPU can't execute x86 instructions directly. It needs to break them down into simpler microoperations for execution. Stages streamline this process, allowing the CPU to handle instructions efficiently despite their varying length and complexity. These stages help balance the trade-off between decoding speed and execution flexibility. In essence, the stages optimize instruction flow through that CPU pipeline, reducing bottlenecks and improving overall performance. So let's go into what these stages are. We have the first stage, which is the instruction fetch stage. Its goal is to retrieve instructions from memory. The CPU's instruction fetch unit retrieves instructions from the L1 instruction cache. If there's a cache miss, it moves to L2, L3, or main memory, RAM, stalling the pipeline. This stage relies heavily on branch prediction to preload instructions and minimize delays. Malicious instruction patterns can be detected here through anomalous cache activity. Attackers may attempt cache-based side-channel attacks during instruction fetching. The second stage is the instruction pre-decoding stage. The goal of this stage is to identify instruction boundaries. x86 instructions are variable length from 1 to 15 bytes, like we mentioned, so the decoder must first locate where each instruction begins and ends. The pre-decoder scans the fetched instruction bytes, identifying prefixes, opcodes, mod RM bytes, and immediate values. Now, to explain what mod RM bytes are, that's a single byte in certain x86 instructions that provide additional information about operands. It's used to specify addressing mode, how to locate operands, register operands, which CPU registers to use, and memory operands, how to reference memory addresses. The x86 architecture supports flexible operand types, like we mentioned, registers, memory addresses, or immediate values. The mod RM byte helps the CPU interpret these operands correctly during instruction decoding. Without the mod RM byte, the decoder would struggle to determine which registers to use, how to access memory if it's required, and whether additional bytes like SIB bytes are needed. The mod RM byte is 8 bits, 1 byte, and divided into 3 fields. You've got bits 7 and 6, which is mod, the addressing mode. Bits 5 through 3 is reg, the register operand. And 2 through 0 is RM, the register memory operand. SIB, that I mentioned, that's scale index base bytes. And key challenges include prefixes like operand size override or segment override can slow this stage. Too many instruction prefixes can cause decoding stalls. Let's break down a few key components here to fully understand this. What's an operand? What operand size override does? What a segment is, and what segment override does. An operand is a value or memory location that a CPU instruction operates on. So like we mentioned, it could be immediate values, registers, memory addresses. The CPU uses operands to perform calculations, memory loads and stores, and logical operations. For an operand size override, x86 instructions typically default to a specific operand size based on the operating mode, like 16-bit or 32-bit or 64-bit. Operand size override prefixes allow the CPU to use a different operand size than the default. So the 66 prefix signals operand size override. It switches between 16-bit and 32-bit operand sizes in legacy mode and between 32-bit and 64-bit sizes in 64-bit mode. The CPU's pre-decoder must identify the prefix, so it can slow decoding, adjusting the instruction length and reconfiguring the decode logic for different operand sizes. It adds complexity to instruction decoding and increases decode time, especially in tight loops. The x86 prefix forces the decoder to modify its internal settings to handle 16-bit operands, for example. Excessive operand size overrides can cause performance degradation if not used carefully. Now for segment, in x86, memory is divided into segments for historical compatibility with older x86 models. Segments define memory regions for code, data, and stacks. In protected mode, there are 6 segment registers. You have the CS code segment for executable instructions, the DS data segment for general purpose data, the ES extra segment for additional data, the FSGS additional segments, often used in thread local storage, and the SS stack segment for stack memory. Segment override prefixes instruct the CPU to use a different segment register than the default. Segment overrides use specific 1-byte prefixes. 2E use the CS register, 36 use the SS register, 3E use the DS register, 26 use the ES register, 64 use the FS register, 65 use the GS register. It slows decoding because the decoder must apply the override and adjust memory calculations accordingly. Segment overrides increase decode time by forcing the pre-decoder to identify and apply non-default segment registers. Frequent use of segment overrides can clog the decode pipeline, and malware often uses unusual segment overrides to obfuscate instructions. And too many instruction prefixes can cause decoding stalls, as these prefixes add extra bytes to instructions, requiring the decoder to spend more time identifying instruction boundaries and adjusting settings before it can proceed with decoding. An instruction prefix is a special byte placed before an x86 instruction that modifies how the instruction is interpreted by the CPU. Prefixes are 1 byte long and can alter instruction behavior in areas like operand size, 32-bit versus 16-bit, address size, 32-bit versus 64-bit, segment selection, like using the FS register instead of DS, instruction locking, like atomic operations, and SIMD instruction modes. Prefixes are used for backward compatibility with older 86 code and for optimization for specific operations like lock prefixes for atomic memory instructions, and for specialized instructions like rep for string operations. The x86 instruction decoder relies on a pre-decoding stage to identify instruction boundaries, the alteration of instruction behavior, and instruction complexity. So this is why they impact decoding performance. When prefixes are excessive, the pre-decoder must process more bytes before it can identify the start and end of each instruction, and before it can apply the correct operational settings for the CPU to execute the instructions correctly. A decoding stall occurs when the CPU cannot decode instructions fast enough to keep the pipeline full. The CPU pipeline relies on a steady flow of microops. If the decoder takes too long to handle prefix-heavy instructions, the pipeline stalls, meaning execution units sit idle waiting for instructions to decode. Decoding stalls are common when instruction prefixes are overused, like complex x86 instructions with multiple override prefixes, or when cache misses occur in the L1 instruction cache, or when the CPU switches modes, like from 62-bit to 32-bit. Instruction prefix misuse can be a sign of malicious behavior. Malware authors use excessive or unusual prefixes to obfuscate payloads. Prefix anomalies can trigger decoding stalls that disrupt performance or leak timing information in side-channel attacks. Security tools like Sysmon or Intel's Perf can detect unusual prefix usage, helping to identify malicious code. So in x86, memory is divided into segments for historical compatibility with older x86 models. Segments define memory regions for code, data, and stacks. A stack is a last in, first out, LIFO data structure that the CPU uses to manage function calls, local variables, and control flow information. And a stack in computing, as I mentioned, that's a specialized memory structure operating on that LIFO principle. Last in means the most recently added item is the first one retrieved. First out means the earliest items added stay deeper in the stack until newer items are popped off. In x86, the stack works by the CPU uses the stack to store temporary data like function call return addresses, local variables, register states during context switches. In x86, the stack grows downward from higher memory addresses to the lower one. And the key registers involved are the ESP and the RSP, the stack pointer, pointing to the top of the stack, and the EBP, the RBP, the base pointer, anchors the base of the current stack frame. Stacks are frequent targets of exploitation due to their predictable behavior. Buffer overflow attacks are overriding stack memory to execute malicious code, like stack smashing. ROP, return-oriented programming, is manipulating stack return addresses to hijack program control flow. Side-channel attacks are analyzing stack-based cache behavior to extract sensitive data. These stack attacks are mitigated by things like stack canaries, which is a random value placed between local variables and return addresses, by using ASLR, which is address space layout randomization, to obfuscate stack locations, and with compiler-based protections like fstack protector. Now, as we said, malware can obfuscate payloads by misusing instruction prefixes. Obfuscation involves intentionally making code harder to read or analyze. A payload is the malicious component of the malware that performs harmful actions. By misusing instruction prefixes, attackers can conceal malicious instructions from security tools and analysts. They can disrupt static analyses, and ultimately the point is to evade detection mechanisms. One of the points is. So you'll hear obfuscate a lot. I always have a very difficult time saying that word. And just understanding that it means intentionally disguising or complicating information to make it difficult to understand, difficult to analyze, and difficult to detect. In cybersecurity, malware developers use obfuscation to hide malicious code from antivirus engines, static analysis tools like IDA-Pro or Ghidra, and dynamic behavior monitors like Sysmon. Plain text code is a clear road sign, but obfuscated code is like a sign covered in graffiti. It's still there, but you can't really see what it says, so you don't know which way to go. That payload, you'll hear that all the time, that malicious component of malware executing harmful actions on a system. Payloads can perform tasks like exfiltrating sensitive data, encrypting files for ransomware, installing backdoors for persistent access, manipulating system behavior to disrupt operations. The delivery mechanism is how the malware is delivered, like via attachment or exploit kit, but the payload is the malicious code that executes the attack, like a keylogger, ransomware binary, or botnet implant. So an example would be a malicious file named invoice.docx, like a Word document file, might contain a delivery mechanism, which is that malicious macro, but the payload is the actual command to download and execute the ransomware. Malware developers use obfuscation techniques to hide malicious payloads from detection tools, like static analysis tools rely on pattern matching to detect malware signatures. So obfuscation will break these patterns, delaying and preventing the detection. They use common techniques for obfuscation like instruction prefix misuse, prefix confusion, junk code insertion, control flow flattening, packers and cryptors like UPX, and encryption of strings like obfuscating API calls. The x86 architecture supports instruction prefixes for legitimate reasons, like operand size changes or segment overrides. But malware authors misuse these prefixes to disguise their malicious code. They might use redundant prefix insertion, where unnecessary prefixes are added to confuse the disassemblers, and disassemblers like IDA-Pro struggle to identify those instruction boundaries. Now, decoding anomalies are unusual or suspicious behaviors observed in the CPU's instruction decoding process. These irregularities might signal malicious code obfuscation, cache-based side-channel attacks, or exploit attempts targeting CPU optimization features. When a cybersecurity analyst is looking for these decoding anomalies, they might look for excessive instruction prefix usage. Since normal applications use instruction prefixes selectively, if they see a flood of instructions with redundant prefixes, that's a signal there. A high occurrence of operand size 66 or segment override 64 and 65 prefixes, and unexpected instruction boundaries due to prefix misalignment. If they say abnormal cache miss patterns, where normal workloads are exhibiting predictable cache miss patterns. Cache timing attacks like flush plus reload create those suspiciously high L3 cache misses. So the anomaly they might be looking for might be that spike in L3 cache misses after execution of cryptographic operations. And they'll be looking for irregular micro-op queue activity. Modern CPUs cache micro-ops to avoid repeated decoding, but malware abusing speculative execution would disrupt that micro-op queue behavior. So the anomaly they're looking for is potentially a sudden, uncharacteristic micro-op flush, or flushes or queue overflows in otherwise stable applications. And they use the monitoring tools like perf and sysmon and so on. And tools like Ghidra, IDRPRO, and Radare2 are used to inspect instructions for unusual prefix patterns. They'll look often for repetitive or inconsistent prefix usage. Perhaps excessive 66 prefixes on instructions that don't require operand size changes. Unusual segment override prefixes like 64 for FS when the application normally uses DS. They might perform behavioral analysis in sandbox environments like Cuckoo Sandbox, which can observe CPU behaviors when executing potentially malicious code. And they'll track patterns like cache access timing irregularities, micro-op queue contention following specific instruction execution, and excessive segment override without functional necessity.